Hello, Geometry. This lesson is titled Proving that a Quadrilateral is a Parallelogram. So again, this is going to be focusing on proofs mainly on this section. Now we have a theorem here to start out with, Theorem 6.5. It says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral must be a parallelogram. So let's go ahead and prove that theorem right there. Again, if both pairs of opposite sides are congruent, then it must be a parallelogram. So that's what we're trying to prove. So we have our two-column proof here. We have our statement and our reason. We always start off with the given. So we have Wx is congruent to Zy. Pardon the handwriting. We also have Xy is congruent to WZ. Now that is already marked out for you, which is nice. I'm sorry about that. And again, the reason why we know that is because that is what is given to us. Now the question is, what do we do from there? Well, notice we have this diagonal going across from X to Z, joining those 2 points. Well, notice that it's broken up into 2 triangles, and both of them share XZ. So we always want to look to see if they have a shared side, which in this case they do. So we do know that XZ is congruent to itself, and that is the reflexive property. Okay, the reflexive property. So if I mark that now, you'll notice that I have three pairs of sides that are congruent. So we can go ahead and say those 2 triangles are congruent. So we could say triangle XWZ is congruent to triangle ZYX. And the reason is because of side, side, side. Okay? Now we're not done, because again, what we're trying to ultimately prove here is that that is a parallelogram. Well, what do we have to do in order to prove that? Well, a parallelogram, we know that opposite sides are parallel. So if we can prove that both pairs of opposite sides are parallel, then that proves that it's a parallelogram. Well, because we've learned about CPCTC, we know that since the 2 triangles are congruent, we could say that these 2 angles would be congruent to each other. And in like manner, we could say that these 2 angles are going to be congruent to each other. So let's go ahead and write that. We could say angle WXZ is congruent to angle Y, I forgot the angle mark, to angle YZX. And again, because corresponding parts of congruent triangles are congruent. Since we've proven that the triangles as a whole are congruent, it proves that each corresponding part will be congruent. And again, in like manner, we could say the other 2 pairs, the ones we marked with 2 marks, are congruent. So let's go ahead and write that. So we could say angle YXZ is congruent to angle WZX because of the same reason, CPCTC. Now, since those are congruent, notice when we've dealt with alternate interior angles before, and it says if alternate interior angles are congruent, that proves that the sides are going to be parallel. So, that is what we can say. We could say now that XW is parallel to YZ, and in like manner also we can say XY is parallel to WZ. And the reasoning behind that is the converse, and again this is stuff that we've done, the converse of alternate interior angles theorem. It says if alternate interior angles are congruent, then it says that the sides must be parallel. Okay? And lastly, we always want to get to what we're trying to prove. We're trying to prove that WXYZ is a parallelogram. And the reason behind that, well, that's the definition of a parallelogram. If we know that opposite sides are parallel of quadrilateral, that means it has to be a parallelogram by definition. Okay? Again, I apologize for the wonderful handwriting, but hopefully you guys are understanding how we're coming up with this proof. Okay, again, we did side, side, side. Therefore, we can say the corresponding parts are congruent, and if alternate interior angles are congruent, the sides must be parallel, which means it's a parallelogram. Okay. Now here it says if both pairs of opposite angles of quadrilateral are congruent, then the quadrilateral is a parallelogram. Same thing, but we're talking about opposite angles, and we'll get to that later. Okay, so if opposite angles, so if I give you a quadrilateral, and you know this angle and this angle are congruent, and these two angles are congruent, the whole shape, the whole quadrilateral must be a parallelogram. Here comes another proof. It says if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So, we have here, again, if the diagonals, so in this case BD and AC, if they cut each other in half, then the ABCD has to be a parallelogram. So let's go ahead and get started with that proof. Always write the given first. So there we have it. AC and BD bisect each other. Okay. And that is given. Now, if they bisect each other, what can we say? Again, if they bisect each other, that means this BD gets cut in half, AC gets cut in half. So we can actually write that out. So what we can say here is AE must be congruent to EC. And in like manner, we could say BE is congruent to DE. Why? Because that's what a bisector does. So that is the definition of a bisector. Actually, I'm just going to type that out to make it easier for you. So there you go, definition of a bisector. Now, what else can we say? Well, we have two pairs of sides. So now we need to come up with a third bit of information. Well, if you look at the sides that we were given, we have here two triangles that are being used. Okay. Well, we also learned that vertical angles will always be congruent to each other. So that also is what we can write. So we can say that angle BEA is congruent to angle CED. And why is that? Because vertical angles are congruent. Okay? Now from there, we can say that those two triangles are actually congruent to each other. Now that we have enough information, so we could say here that triangle BEA is going to be congruent to triangle CED because of side angle side. Okay, we have side angle side in this case. And therefore, all their corresponding parts are going to be congruent. And remember what we're trying to prove here. We're trying to prove that it's a parallelogram in which opposite sides are parallel. Well, just like our last two-column proof, if we can prove that the alternate interior angles are congruent, then that would prove that the sides are going to be parallel. Well, now that we know that triangles as a whole are, the two yellow ones are congruent, we could say their corresponding parts are congruent. So I'm going to switch to green here. So we could say that these two angles are going to be congruent. Okay? So we could say angle ABE is congruent to angle CDE. And again, the reasoning for that is going to be, since we know that the triangles are congruent, we know that corresponding parts of congruent triangles are congruent. So that's one pair of congruent sides. Now we can also look at, instead of the yellow triangles, let me just do this really quick. We can also still see that there are two other triangles that we can deal with. I'm going to switch the yellow to these two triangles. Now we're going to follow the same process as we did with the other two, in which we have vertical angles right here. Now, we do the same exact thing. So we have angle BEC is congruent to angle DEA because vertical angles are congruent. And since those are congruent, those triangles as a whole will be congruent to each other. So we can go ahead and say now that triangle, not just angle, but triangle BEC will be congruent to triangle DEA because of that side angle side. And therefore, again, just like we did in this section, we follow the same pattern here. We know that BC and AD, oh, sorry, not the sides, we're looking for the angles. We know that these angles right here are going to be congruent to each other. So angle CBE is going to be congruent to angle ADE because of CPCTC. Now what we've proven, again, is that we have two pairs of parallel sides that are alternate interior angles. Well, if alternate interior angles are congruent, then that proves that the sides are going to be parallel. So we can conclude that AB is going to be parallel to CD, and we can also say that BC is parallel to AD. And why is that? Well, that is the converse of alternate interior angles theorem. Okay, again, if alternate interior angles are congruent, the sides must be parallel. Now we can say that the shape as a whole is going to be a parallelogram because opposite sides are parallel. So ABCD is a parallelogram. The reason why? That's the definition of a parallelogram. Opposite sides are parallel. Now, fortunately, because we've gone through these proofs, now we can trust in them, and we can go ahead and apply that when we have to solve for variables. We're going to do that on the next page here. One last theorem. It says if one pair of opposite sides of a quadrilateral is both congruent and parallel, so you only really need to know one pair is congruent and parallel to each other, then the quadrilateral is going to be a parallelogram. So now we get to actually use this to apply to some variables. So we have a parallelogram here, MLPN, well, a quadrilateral. For it to be a parallelogram, what does the value of x have to be? Well, we learned that if the diagonals bisect each other, then it's a parallelogram. So let's go ahead and set up those equations. So we have here, let's go green. We have 2y minus 7 is equal to y plus 2. Again, on alternate sides of the intersection, they're going to be congruent to each other. So now we can solve for y. We're going to subtract y from both sides. So that gives us 1y minus 7 is equal to 2. Plus 7 on both sides, you get y equals 9. Why was that important? Well, because notice it wants x. But if we set up the other equation, it's 3x is equal to y. So we had to find y first. You can't really solve an equation that has two variables by itself. You need to be able to plug something in to get down to one variable. So now instead of saying y, we could say 9. So if you divide by 3 on both sides, you get x is equal to 3. And there you have it. Again, the diagonals of a parallelogram will bisect each other. Here, find the values of A and C for which PQRS must be a parallelogram. Now, it's important to understand what you're dealing with here. C has to do with the sides. A is dealing with the angles. So let's do C first. Let's get done with the sides. Now, we know that opposite sides of a parallelogram have to be congruent. So therefore, we set the opposite sides equal to each other. Now we're going to subtract C from both sides. So we get 2C minus 3 is equal to 1. I'm going to add the 3 over. So I have 2c is equal to 4. Divide by 2. I have c is equal to 2. So we're done with the c's. But the thing about the a's is that if it is a parallelogram, then consecutive angles in a parallelogram are always going to be supplementary to each other. So we would set this up a plus 40 plus the other a has to add up to 180. So I'm going to subtract the 40 and combine like terms. So I have 1a plus 1a, which is 2a, is equal to 140. Divide by 2 on both sides. A must be 70. There you go. Again, opposite sides are congruent. Consecutive angles, meaning not opposite of each other, in a quadrilateral, or a parallelogram, are going to be supplementary to each other. Okay? And I believe that's all we got. So good luck with that. I hope that helped. Again, dealing with some proofs, proving why these theorems work so that we can trust it when we have to actually solve for variables. Okay? Good luck.